And essentially, when you're forming a combined event, you multiply. When there's an alternative number of ways of performing the combined event, then you add the alternatives. And that sounds pretty simple, but it's not. It requires practice. It really does. Let me go through a couple examples and maybe touch upon something similar to one of the homework examples that you had, and maybe consider another question or two, and then we'll build on this today. Okay, so remember when we talked about sets? We suppose we had the set A2 up through A sub n. And the question I asked then was, how many different subsets are there for a given set? Now, this set has n elements, right? The number of elements in the set A is n. So the question is, how many subsets does it have? Now, there's a very, very clever way of figuring this out. If you look at every subset, think of any element in the subset as having n spaces. For example, if I had a subset of 3, there might be n spaces that we have to fill up. And each space, for example, in this one, for the element A1, either A1 is there or A1 is not there. If you look at any particular subset, either A1 is there or it's not there. So how many choices do we have for the presence of A1? 2. Similarly for A2. If A2 is not there and all the other elements are there, then it's a subset of size n minus 1. So for each of these elements, there are 2 choices. And the combined event is all of them. So we have 2 to the n possible subsets. So if you think of the 2 choices being present and not present, if I had, say, A2, A4, and A11, then this would just be a subset containing just these 3 elements and no others. So this is a very clever way of counting the number of subsets in a set. A little later today, I'll show you another way of getting this. So if you think about it, in every single subset, either each element is there or it's not there. So it's we have 2 to the n possibilities. Okay. Consider another example, which is very similar to one you did for homework. Suppose I have 3 boys and 4 girls, and they're going to stand in a line to take a photograph. Okay? I think this was problem number 26 in the homework. But there are parts of this that are a little tricky. So in how many ways can they stand for a photograph? Well, there are 7 spaces. I can put any of these 7 people in the first position, then 6, then 5, then 4, then 3, then 2, then 1. So if I wanted to answer that question, the answer is 7 factorial, whatever that is. Let's see, 6 factorials. I don't know what that is. I have to multiply it out. Now, suppose I wanted the boys together. And I wanted all the girls together. You notice I can go boys and girls, or girls and boys, so I'm double my answer. Well, suppose all the boys are here. And there are 3 boys. How many ways can I place these boys? 3, 2, 1, right? And how many ways can I place the girls? Well, there are 4 of them. 4 times 3 times 2 times 1. So if I did this, it would be 4 factorial times 3 factorial. That's going boys and girls. Couldn't I just as well go girls and boys? This would again be 4 factorial. This would then be 3 factorial. So I have 2 alternative ways of positioning boys and girls so the boys are together and the girls are together. So my answer would be 2 times 4 factorial times 3 factorial, and that's easy enough to work out if you want an answer. Okay, what if boys and girls alternate? Well, now you got to be a little bit careful. I can't start with boys. Well, I suppose I did. I'd have to have a boy here, a boy here, a boy here, and a boy here, right? But how many boys do I have?
You have 3.
3. So I can't do this, correct?
Correct. You could do it with the girls.
That's right. So, but I can do this. I can go girl, 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 girl. I have 4 choices for the first girl, 3.
Then 2, then 1. And then you're going to
And then
have
for
3,
the
2,
boys,
and
I
1.
have 3, 2, 1. And I could write this 4 factorial times 3 factorial if I want, or 4, 3, 3, 2, 2, 1, 1. So that was pretty straightforward. So now let's put a little bit of a twist. Which one do I have to dig? Okay. In part D, we want one particular boy and girl insist on being together. Okay, so here's what you do. We have, what was it, 4 girls and 3 boys, right? So let's choose one of the girls and one of the boys and think of them as being a single unit for now. And then what's left will be 3 girls and 2 boys, right? So think of this as being a special unit. So I have 5 and the special unit is 6, right? So if I think of this as being one unit, essentially I have 6 items. And that would be 6, 5, 4, 3, 2, 1. But how many ways can I form this unit? By the way, there were no other restrictions here. Order in which I put all the other boys and girls didn't matter. Now I have 2 I can go girl, boy, or I can go boy, girl. So I can double that answer. We have an alternative, and this would take care of that case. Now, what if these boy and girls don't want to be together? Was that E? And one particular boy and one particular girl must not be together. Well, we know altogether there were 7 factorial. There were 7 factorial possibilities. Was that right in the first part? Yeah. So this is the total number of possibilities, total number of ways they can stand in a line. If I subtract from that the answer to the previous problem, then what's left are the number of ways they're not together. So I can write this answer a little nicer, by the way. Factor out the 6 factorial. And then write the answer as 5 times 6 factorial. That's if I wanted to make my answer look pretty. Okay. So that was an interesting result. It sort of shows you what was nice about this last part. It shows you how to do a problem indirectly. Let me give you another example of that, and then I'll see if there are any other particular requests that you have. This was a harder problem. You had to think about it a little bit more carefully. I didn't find it too hard because I've done this problem a million times. I knew the approach, but if this is the first time you're handling a problem like this, it could be rather difficult.
Professor, going back up a little bit. Sorry for interrupting. The 7 factorial, right?
That was the total number of ways 7 people could be standing all line. Yeah.
I just lost you right when you got 7 times 6 factorial.
Oh, 7 factorial is the same as 7 times 6 times 5 times 4 times 3 times 2 times 1, right?
Yeah.
Stop anywhere I go with a factorial. For example, 18 factorial, if I want, I can write it as 18 times 17 times 16, and then what's left would be 15 factorial, right?
Oh, yeah, I see what you did. All right.
Okay.
That's actually really cool. I haven't thought about it that way.
Okay. So let's suppose I have 9 married couples. I just want to show you, and let's assume for simplicity, by a married couple, I mean a male and a female. Okay? So here's a question. How many couples, no, let's say it differently. How many ways may a male dance with a female, meaning, okay, if no man is to dance with his wife? Okay, now you'll see this is a pretty trivial problem, but I want to show an idea here. Anybody want to venture a guess? Or maybe not a guess, an answer?
I mean, probably 8 factorial,
Bad answer.
because what would happen is you just take,
You're thinking wrong. I'm not filling up 8 spaces now, or 9 spaces.
oh wait, that's true.
So I'm really asking how many different couples are possible? A couple consists of how many spaces?
I mean, you have 9 married couples,
So
so
combined event would be, combined event is containing 2 people.
yeah.
Okay, so firstly, altogether, let's do this problem 2 ways. Okay, method 1. Well, let's suppose I choose a male first. How many choices do I have for a male? Okay, now we'll choose the female. How many choices do I have for the female if no man is to dance with his wife? Okay. So the answer to this problem would be 72. Now here's another way of doing the problem, the indirect method. Sometimes the indirect method is very helpful. How many couples are there in all? Well, there are 9 men, right? And there are 9 women. So there are 81 couples in all. How many of these couples are married? How many?
I'm assuming all of them because it says
Told you
9
9 of
married
them,
couples.
right?
Yeah.
There are 9 couples. Oh, did I say that up here?
Yeah.
Okay. So if I subtract the 9 married couples from the 81, what's left?
72.
72. Notice there are 2 ways of doing the problem. I actually did this above when I looked at this problem. Where was it? Up here? What I did was I said there were 7 factorial couples in all. Subtract when the 2 people were together. And so I got sort of the complementary event. So there are different ways about thinking about problems of this, of getting the combined event. How do you get good at it? You do lots of problems. It requires practice. Were there any particular problems that bothered somebody immensely? And if you don't want to ask it now, you can send me an email. I'll work it out and I'll just send it to everybody. Don't be shy.
I mean, I had a problem with number kind of 21, actually. No, actually it was 22, my bad.
Which
It was
one?
with the jumbos. Number 22 on page 36.
Okay, how many jumbles does 4 have?
Yeah, I had a little bit of problems with that one.
Okay, so, well, how many letters are there? Notice they're all different. That's important. 1, 2, 3, 4, 5. So I have 7 spaces, right?
Yes.
I can put any 7 letters here, then 6 and 5 all the way down to 1. That would be 7 factorial. And what number is this again, please? 20, yeah. How many in which the vowels and consonants are to alternate? So let's look at this. How many vowels do I have? I have 3 vowels. And I have 4 consonants, right? I cannot start with a vowel because I only have 3 vowels. If I did, I would have vowel, 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 and then I can't do this. So I have to start with a consonant. I have 4 choices here, 3, 2, 1. And then I can put the vowels in, 3, 2, 1. And if you want, you can write this as 4 factorial times 3 factorial. If you want to work it out, 24 times 6, which is what, 144? Okay. And was there a third part to this one? How many begin with an D and end with an E? Okay. If it begins with a G, there's only one G, so I only have one choice here. If it ends with an E, means the E goes here, I only have one E, so there's only one choice here. So I use up 2 letters, how many letters are left? 5. There was no other restriction. 5, 4, 3, 2, 1. This turns out to be multiplying together 120. Is that okay? Does that answer
Yeah.
your question?
Yeah, it did.
Okay. Onward. So let me get my book out. By the way, am I now correct in assuming that everybody now has the text? Is there anybody who doesn't have the text just yet? All right, send me an email and I'll send you this section. We don't meet for a week next week because Monday is Labor Day and Wednesday is a holiday. So you should have it by then. Okay. So now I want to talk about the topic at hand. And in fact, we've done part of it already, but permutations and combinations. So let's suppose I have 5 names. Albert, Betty, Charles, Dina, and Edward, okay? And I asked 2 questions. Question number 1. How many ways may I choose 3 of them to stand in a line? And the second question is, in how many ways may I choose 3 of them to form a committee? Questions look very similar, don't they?
Yeah.
So are their answers the same or not? That's what we need to
I feel like it's gonna be a little bit.
So we need to understand the difference between these 2 questions. So let's look at the first one. In the first one, suppose the people I chose were A, C, and E. If they're standing in a line, that's a different ordering than A, E, C, isn't it? Even though it's the same 3 people, the order which I put them in a line, say for taking the picture, it matters. So notice in this example, the order in which I choose the people matters. For the same people, just moving them around a little bit gives me a different line. Now in this group, whether I choose A, C, and E, or A, E, and C, I've chosen the same committee, haven't I? So whether I choose A, C, and E, or ECA, or AEC, or whatever, it's still the same committee. So the order does not matter. So let's define, and by the way, we know the answer to the first problem. There are 3 positions, right? I have 5 people I can choose for the first position, 4 for the second, 3 for the third. The answer to this problem, by the way, happens to be 60. I'm not really interested in the answer just yet, but we certainly know how to do the problem. So let's make some definitions. An arrangement in which order matters, and now you understand what I mean by the order, is called a permutation. So that was sort of example one. An arrangement in which order does not matter is called a combination. And we'll look at these very shortly. We've already learned how to do permutations. I'm going to give you a formula which is useless for permutations in a couple of minutes. The way to do permutations is just by drawing the little boxes or little spaces and fill them up. But we'll have a formula anyway for those people who love formulas, but they're not very useful. I will develop a formula for combinations that is very useful. Okay, so we have these two different entities. Now, let me just talk about what we just had a minute ago. Suppose I have the letters A, B, C, D, and E. Observe, I can have A, B, and C, A, B, and D, A, B, and E. 1, 2, 3. I'm going to get 10 altogether. Let's go some more. B, C, and D. B, C, and E. Oh, by the way, I left out somewhere. I have A, C, and D. I have A, D, and E. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. Well, I list them all. I don't want you to spend the time. I list them all, by the way, on page 41. So I got ABC, ABD, ABE, ACD, ADE, BCD, BCE, BDE, BDE, and CDE. And notice if I have ABC, I also have ACB. And if I have ABC, I also have BCA. And I also have BAC or CBA or CAB. Notice for each of these, so I have these 1, 2, 3, 4, 5, 6, 7, 8. I'm missing one, okay, from my list, whichever one it is. I have these 10 different committees, right? But if I was thinking of them in terms of lists, each committee has how many lists? 6. Or 60, I could put them 60 different lines. So notice one of the answers is a multiple of the other. By the way, why are there 6? Because if I have 3 letters, in how many ways can 3 letters be jumbled? 3 factorial. So notice each group, each box group has 3 factorial different lists that I can make. So let's introduce some notation. We'll come back to this problem. Given n items, and we choose R, which is smaller than n, and we choose of them. The number of possible permutations is denoted by P and R. By the way, some books write it differently. Some books write N, PR, or other variations, but it's pretty obvious what it is. The number of combinations is we'll denote it two ways. One way, which I don't like to use, is CNR. Some other books use NCR. And the other notation is the binomial coefficient notation, which I prefer. You'll see why soon enough, is this one. So notice in the problem that I did a minute ago, I had 5 names and I was choosing 3. I would have designated the answer as P53. That's the number of lines and number of lists that I can make if I choose 3 objects from the 5. And the number of combinations, I would designate it either by this symbol or this symbol. Either one. And by the way, we saw above that P53, basically all I had to do was the following. 5, 4, 3. I have 5 choices for the first position of the list, 4 choices for the second position of the list, 3 choices for the third position of the list. And by the way, this happens to just be 60. But notice the following. If I want to develop a formula, I can rewrite this as 5, 4, 3. If I add a 2 and a 1 here, I put a 2 and a 1 here. This is a 5 factorial. And 2 is related to 5 and 3 by so in fact, if I want to do more generally, if you look at the pattern, I can actually derive write down a formula here. Now that's not a really impressive formula. I want to point that out. But if there are some people who like formulas. By the way, notice I could have written this as also, if I did the cancellation, n times n minus 1 times n minus 2 times n minus r plus 1. Oh, there are some examples I want to do here. I accidentally closed my book. Okay. That's an r minus 1, by the way, not a plus 1. This is a minus 1. Okay. Now, also notice in the previous problem that I did a minute ago, P53 turned out to be 60, and C, or let's just say N choose R, turned out to be 10, right? So the question is, how are they related? Notice P53, all right, C was equal to C 53. Oops, hold on a second. This was hold on one second. This is 60. This is 10. Now, in order to make these equal, what do I have to multiply the right-hand side by? Right, but why was there a 6? The 6 was the 3 factorial, right? Why was it? Because if you have 3 letters, 3 people in the committee, they can be jumbled 3 factorial ways. So in fact, notice 5 choose 3 can be written as P53 divided by 3 factorial, or more generally, N choose R, or if you like the symbol CNR, is equal to PNR divided by R factorial. Now, remember what PNR was? I'm sorry, N minus R factorial. Yeah, we're good. And now remember, what was P comma R? That was equal to N factorial over N minus R factorial. So if I plug in, I get the following useful result, or if you like, CNR, is equal to N factorial times N minus R factorial times R factorial. Okay. So for example, oops, sorry about that. So for example, if I wanted to compute the combination 7, 4, and by the way, this could say, how many committees of 4 can I choose from 7? And the other notation would be this. According to this formula, it's 7 factorial divided by 4 factorial times 7 minus 4 factorial. Notice, by the way, the numbers in the denominator add up to the numerator. So 4 plus 3 is 7. So if I want to compute this, what I would do is I write it 7 times 6 times 5. I stop at the largest number in the denominator. Then I have 4 factorial. And then I have 3, 2, 1. The 4 factorials cancel. 3 and 2 is 6. I get an answer of 35. So computing these combinations is pretty easy. Notice I can interpret this very nicely. I can interpret this as the answer to the following question. How many committees of 4 can I choose from 7 people? And the answer is 35. Without doing any work, can anybody tell me what the answer to this problem has to be? Well, if you do the work, you'll see you're going to get 7 factorial divided by 3 factorial, 4 factorial, which is the same as this right here. So this is also going to be 35. But there's a simpler reason for this. In fact, it's going to give us an identity. If I have 7 people, every time I choose a committee of 4, how many people am I leaving out? Right. So that means every time I choose a committee of 4, I'm simultaneously choosing a committee of 3, the number of people I don't choose. So the number of ways I can choose a committee of 4 from the 7 must equal the number of ways I can choose a committee of 3 from the 7. And in fact, more generally, we have the following identity. Now that's an interesting result. And if you interpret it, it says the number of ways I can choose a committee of R from N is the same number of ways I can choose a committee of N minus R from N. That's pretty neat. Okay, so computationally, this is pretty easy. By the way, answer the following question. I'm sorry? No, it's not a community property, not at all. We could actually work this problem out, right? But if I have n people, how many committees of one can I choose from n people? If I have 17 people, how many committees of one are possible?
17.
17. Right? You guys, there's a little noise in the background. Somebody's mowing his lawn next door. It'll disappear soon. Let me know if you can still hear me. Let's reverse the question. If I have n people, how many committees of size n are possible?
1.
If I have 20 people, how many committees of 20 are possible?
1. 1.
Just one, all 20. Now, by the way, if I want to work this out, so clearly from the understanding what a combination is, from what a combination is, we understand why this answer has to be 1. Now, let's suppose we use the formula. We know this answer must be 1. Now, this term cancels this term. N minus n is 0, 0 factorial. In order for us to get the correct answer, what must 0 factorial be?
1.
Must be 1. So you see why when I define 0 factorial, we needed to define it to be 1. By the way, notice if I use this identity, this must also be 1. If I put R as n choose n is 1. If R is, so again, if R is n over n is 1, n minus n is 0, n choose 0. So again, I want to point out the following. This gives you the number of ways we can choose n people from R. Choose R people from n, sorry, where order matters. And CNR, or n choose R, choose R from n, where order does not matter. By the way, think of C as committee. A committee where everybody has the same responsibility, order doesn't matter. If I choose ABC or CBA or whatever, it's still the same committee. Order doesn't matter. How would order matter? Suppose I chose a committee of 3, but one was to be the president, one was to be the vice president, one was to be the secretary. Then it would matter. Then it would be a permutation, not a combination. Let me walk through an example or two with you. Where is that?
Wait, so Professor, could we also use that same question that you used before?
I'm sorry, say that again, please.
Can we use that question that we used before? We have like an arrangement of like, oh wait, never mind.
Okay, well, if it comes to you, let me know. So if you look in the text, I don't know if you have the text with you, I'll read it out loud. In example 1, I asked the following question. Assuming I can read my text. In each of the following, determine the appropriate symbol which represents the answer to the question. We can go figure it out in more. In how many ways may 7 students be chosen from a class of 12 to stand in a line. Does order matter?
Yes.
Yes, because if I put A and then B and B and then A, it's a different ordering. So the answer to that problem would be if you're using the symbol. Of course, what I would do is I would just draw 7 spaces and go 12, 11, 10, 9, 8, and so on to do the problem. What about if the 7 are 7 from 12 to form a committee? Does order matter?
No, in that case, order does not
No, so it
matter.
would just be 12, choose 7. By the way, this is called, and you'll see why in a couple of days, a binomial coefficient. That's what we call this symbol. Again, you can use either symbol. I prefer the first one. What about the first, second, and third prize to be awarded in a beauty contest in a group of 100 people? First, second, and third prize from 100 people. Permutation or combination? Right, because order matters now. It matters who gets the first prize, who gets the second prize, who gets a third prize. Okay. 5 cards to be chosen from an ordinary deck of playing cards of 52 cards. Choose 5 cards from 52. Permutation or combination?
Permutation,
Why?
because you're not giving like specific cards, you're just choosing random cards out of the deck.
No, your reasoning
Yeah.
isn't right. If I have 1, 2, 3, 4, 5, or if I have 5, 4, 3, 2, 1, do I have the same hand?
Yeah,
Order matter in which I choose the cards?
no, it doesn't matter.
No. So therefore, by the way, this is a pretty big number, like 2,900,000 and blah, 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 blah. If you want to work it out. It's a lot of possibilities. It's over 2 million possibilities. Okay. I just want to talk a little bit about multiplying things out and then consider a simple example or two. And then this chat will talk a little bit. Okay. So never use I never bother with permutation formula. It's a waste of time. If I want to choose, for example, 5 people from 7 to stand in a line, of course you could say this, but I much prefer to go 1, 2, 3, 4, 5. I can choose any of 7 for the first position, then 6, then 5, then 4, then 3. I don't need a formula for the problems involving permutations. In fact, it's usually harder when there's a more complicated problem, as we'll see soon enough. But for combinations, I do. Combinations are going to be useful. So let me just do some calculations with you with some combinations. Suppose I want to choose 12 from 43 people, a committee of 12. Well, then the answer would just be 43 choose 12. Well, let me show you how we'd actually do the calculations. This would be 43 factorial. This would be 12 factorial. And what would it be? 31, is that right? 31, 41, 40, yeah. So if I were going to calculate this, I would go 43, 42, all the way down to 32. Then I go 31 factorial over 12 down to 1, and then 31 factorial. These two terms would cancel, and then I would simplify this. I don't really want to do arithmetic now. But the calculations are pretty straightforward. So let me consider a non-trivial example involving combinations. Let's suppose I have 8 men and 5 women. Question number 1. How many committees are possible? How many committees of 10 are possible? First question. Well, altogether, notice I didn't impose any restrictions here. Altogether, how many people do I have?
13.
13. And I want a committee of size 10.
10. Yeah.
So I'm asking how many combinations of size 10 can I choose from 13? This would be 13 factorial over 10 factorial times 3 factorial. I'd work this as 13, 12, 11, 10 factorial, 10 factorial, 3, 2, 1. 2 goes 6, 3 goes, kills that. So the answer is what, 13 times 11? Problem solved. Okay, let's change the problem now. How many committees are possible?
11 and 6 probably.
Sorry about that, folks. I wish I could stop that. Here shortly, containing 6 men and 4 women. So now the combined event is the committee, correct? So the committee is going to contain men or women, which means once I choose the number of ways I can choose the men, and once I choose the number of ways I can choose the women, the combined event is their product by the multiplication principle. Okay, well, how many men do I have? I have 8 men. From the 8 men, I need to choose 6. And from the, how many women? From the 5 women, I have to choose 4. So this would give me 8 factorial over 6 factorial times 2 factorial, 5 factorial, I wish I could get the landscaper out of here, but okay. So this gives me 8 times 7 times 6 factorial, 6 factorial, 2 times 1 times 5 times 4 factorial, 4 factorial 1. So this gives me 28 times 5, which is 140. And by the way, if I ask, what's this probability? Even though we haven't talked about probability yet, in total, there were how many committees? There were 13 times 11 committees. Was that 13 times 11? I can't read, yeah. There were 13 times 11 total committees. I'm sorry, 13 times 11. And we have 140 favorable ways of getting this event of 8 men and how many men was it? 6 men and 4 women. This would be the probability. Let me take this one step further, okay? Same group of men. Where are my numbers? I have 8 men and 5 women, right? I'm going to come back to this problem the next time. Well, suppose one of the guys' name is Sam. And one of the women's name is Beth. Okay. How many committees, how many men and women did I have before? Containing 6 men and what was it, 4 women? If Sam and Beth are among the committee members. So if you think about this, you need to have Sam and you need to have Beth, right? There's only one choice for each of those. And then you need 5 more men, 5 from the remaining 7, and you need 3 more women from the remaining 4. So by choosing Sam and Beth, basically, you don't even have to write this part of it down. This is just 1. The problem just becomes 7 factorial over 5 factorial, 2 factorial, times 4 factorial over 3 factorial, times 1 factorial. And that would give you your answer. One last example, okay? Show any set of n elements as 2 to the n subsets. I want to show you another way of doing this problem. So, in fact, let me do a simpler problem. Let's suppose I have 5 elements. I want to look at the total number of subsets. Well, if you look at the total number of subsets, you could have, each subset could have the number of subsets with no elements, 1 element, up to 5 elements, right? The number of elements in the subset. This, of course, is the empty set. And this, of course, is the full set. So let's see. If I have 5 elements, think of each subset as being a committee. For example, if I had a subset of 2 elements, think of that as being a committee of 2, whether I choose A1, A2, or A2, A1, it's the same committee. So from the 5, choose no elements. From the 5, choose 1 element. This would be the number of subsets of size 1. From the 5, choose 2 elements. From the 5, choose 3 elements. From the 5, choose 4 elements. And by the way, there's an alternate number of ways of choosing the subsets. That's why I'm adding. From the 5, choose 5 subsets. Now, if I work this out, I get 1 plus 5 plus 10 plus 10 plus 5 plus 1, which is 32, which, by the way, is 2 to the 5th. In the general case, I would get n choose 0 plus n choose 1 plus n choose 2 up until n choose n. And by the way, I showed you earlier that this has to be 2 to the n. So it's an interesting identity, by the way. Remember sigma notation? N choose k, n going from 0 to n is equal to 2 to the n. That's an interesting identity that we're able to get for free using combinations. Will I ever need that identity? No, but it's pretty. So let's suppose I have a penny, a nickel, a dime, and a quarter. Called penny. So I have a nickel, a dime, a penny, and a quarter in a purse. I stick my hand in the purse and I choose some money. How many different sums are possible? Well, I have 4 elements, right? So the total number of subsets would be 2 to the 4th. But if I'm always drawing, so I know there are a total of 16 subsets here, each of which gives me a different sum of money. If I If I said I always draw a sum of money, that means I'm excluding the empty set. So the answer I would get for this problem would be 15. Okay, just a couple of observations. That's sometimes helpful. We've shown that n choose r is equal to the same as n choose n minus r. And the interpretation we gave for this is number of ways I can choose a committee of r from n must be the number of ways I leave n minus r from n. We know n choose 0 by virtue of this is equal to n choose n, which is 1. That's an interesting result. And this is why we got, in order for this to happen, we have to define 0 factorial to be 1. And I want to derive one other nice result. There may be some others I'll get later, but I want to prove an identity. And this identity is the basis for something called Pascal's triangle, which you may have had when you took algebra. And I may want to use this later. So suppose I have n people, one of whom is Sam. So I have Sam and n minus 1 others. And I want to choose a committee of size r. Well, if you look at every possible committee of size r, there are two alternatives. The committee has Sam in it, or Sam isn't in the committee. Okay, well, I know the number of committees of size r that I can choose is n choose r, right? If Sam is a member, so I have n choose r as a total number of committees I can choose. If Sam is a member of that committee, then I need to choose r minus 1 more people from the remaining n minus 1 people, right? Because I already have Sam, so I only need r minus 1 more people. On the other hand, if Sam is not there, I still need r people. And if Sam's not to be on the committee, I'm choosing them from n minus 1 people. So here's an interesting identity. Now you can actually prove this identity by working all this out. You can work all this stuff out and show we end up at the same result. But notice from a simple argument involving combinations, I was able to deduce this result. Okay, so I'd like you to do for homework the exercises in section 1.4 that are in the syllabus. I'm going to let you go a couple of minutes early today because I have another meeting I got to pop in. I have to zoom into, as they say. If anybody came late today, just send me an email and I'll correct the attendance. We don't meet on Monday because it's Labor Day, and then we don't meet on Wednesday because it's a holiday. The college is closed. So I don't see you for a whole week. Please don't forget this stuff. I'm going to build on this the next time. Anybody have any particular questions before we close up shop today?
Professor, can I ask you a quick question?
You just did. Would you like to ask another one?
Yes, please. Thank you. So as I understood, I registered late. So homework is
I'm sorry,
just
say that again.
as I understood, as I registered late, like before yesterday, like 2 days
Right.
ago. Homework is not mandatory. It's only for us, right? It's not graded.
I don't grade it, but the way
Okay.
when I give you exams, I'll know if you're doing your homework or not.
Yeah, I know. So it's for us to understand.
Okay,
Okay, thank you. So you only graded exams, right?
that's right. But if
Okay.
you have questions about homework, you have to ask me.
What questions? If if I don't understand, or what do you
If
mean?
you don't understand a homework problem, you ask me, we'll work it out in
Yeah.
class.
Yeah, of course. I didn't mean this. I just asked if you are grading it because
Okay,
I
hold on,
didn't.
before I forget, let me just stop the recording.
Okay, thank you.